Do not base your grade in the class based off of a single exam. Right? That's always something that I have to point out. Everybody tries to go through and say, oh, I got a letter grade based off of an exam score. No, you did not. You did not get a letter grade based off the exam score. Your letter grade comes from the accumulation of points both in homework and in projects that have yet to really be started, in addition to the exam. So all of those things are factored into your grade. Don't be jumping to conclusions based off of an exam. Hopefully what you will see, actually I honestly don't remember, in Canvas, there's a couple things that you can take a look at. Number one, Canvas will show you points kind of earned per thing, okay, or per category. Okay? And that's fine, that's usually correct, that's entered in by me. The last thing that Canvas does is Canvas tries to go through and calculate a grade. Canvas is wrong when it calculates a grade, okay? Straight up wrong. There's 2 points when Canvas is correct. The very beginning of the semester, like before it starts, okay, because there's nothing there, and the very end of the semester when everything has been added in. Even then, Canvas will still be wrong because we have a resurrection final, and that final can replace a score. Canvas doesn't do that. I do that. Okay? So the total that Canvas gives you is false, it's inaccurate, don't ever reference it. Okay? I will attempt to hide it, but depending on how you access your gradebook, you can override my hiding of that grade. Okay? To quote unquote fix that, what I have created and will provide after every exam is a grade category. Just gotta find it here. So you don't get to see the assignments like this, but you'll see this post-exam 1 grade within Canvas. That is from me. That is legit. Okay? That's where I see your letter grade right now. Okay? Everybody in the class, I think, is passing. There's a couple cases that are a little borderline. Easy fixes. Okay? So you shouldn't be panicked, at least yet. What we should be trying to do is figure out what went wrong and how to fix that. One of those things, as an attempt to fix that, is I'm providing the opportunity to get points back for the exam. This is something that I went to a conference for, and they provided a whole bunch of kind of information and guidance. We're using it slightly different than they did, because the way they used it, you can see it here with this Unit 1 thing, is they had a whole bunch of quizzes for OChem 1. And they said the first 5 weeks, students had full access to all of these quizzes, and they just had to do, I think, pass. They had to get all of them correct before they were allowed to advance. Okay? Then you could still advance against the instructor's wishes. But as long as you took all of the quizzes and you did well on them, the instructor said, okay, you can take exam 1. If you don't, they say you need to leave. You clearly aren't prepared for that process. I think that's a bit of a stretch. What we're going to use it for exam 1 is ultimately a way to get points back. So if we go through and look at these quizzes, these topics should all look familiar. These are all topics that we have covered throughout the Unit 1. And so these are relatively short quizzes. I didn't actually look to see, has anybody looked at them or attempted any of them? Okay, that's fine. That go through and ask, I think, up to 5 questions, but it hovers around 2 to 3 questions about those topics. All right? What you need to do is get them all right to get the point. Okay? I think Canvas will still score it, but I will score it differently than what Canvas will. When you get them all right and a perfect score, I'll add that point back to your exam score. 1, 2, 3, 4, 5, 6, 7, 8, 9. And maybe even a bonus 1 point for just doing them all. Okay? Or at least attempting them all. Those points then go back to your exam score, and that should bring the exam scores up to a more reasonable average, and make sure that you've had the experience behind those things. Some of the questions ask you to go out and use a drawing software and then enter codes. That is going to take time to get used to. I fully expect that to be problematic, so when you attempt it and encounter those questions, Try it, see what happens, let me know. Okay, and we can kind of work through that together. But you need to attempt it first before I know how bad it actually is. Kind of, sort of. These quizzes are things that I actually wanted earlier on in the semester. That's where we started. Like, I think our first 2 weeks we had small little quizzes in class. I wanted these quizzes to actually be available at the beginning. I just didn't have access to them yet. Okay, now that I have access to them, I'm retroactively giving you access for Unit 1. And for Unit 2, you'll see them pop up where I think they are relevant. Okay, there's a whole bunch going this first week because some of these are reviews talking about the stereoisomer stuff. We talked about that before exam 1, that we're going to talk about them again in this unit to provide that extra experience to make sure you're aware of what's going on with those structures. Kind of, sort of. After that, I think week 7 is where they die out. Yeah, and I would need to actually start making some other ones. Now that I know roughly how someone has structured those quizzes, I can now go through and do something similar. It just takes time. Okay? For each of those quizzes, you get a guaranteed 3 attempts. And it may actually be 4 attempts. All you have to do is ask, and I'll reopen it. I just need to know you need more attempts and know what you're doing to prepare for it. Okay? These quizzes are massively grouped. So there may only be 3 questions, but question 1 has 40 different questions to pull from. So when you retake it, you're going to get a different question. Okay? It's going to be formatted differently. It's going to have different aspects that it's asking on, but it's the same topic. Kind of, sort of. Okay. Hopefully what this will also provide is kind of a little bit more follow along so that you know a little bit more where you're at within the course. So if you're struggling with these, that's probably because you aren't doing enough to figure the content out. Now you need that extra help. That extra help can happen in class and also happen outside of class and office hours, that kind of stuff. Make sense? Questions? Due dates kind of arbitrarily set. For the ones for Unit 2, I set them to be due at the end of that week. So this first set of whatever that is, like 6 or 7 quizzes, is officially due this Sunday. I have no problems moving that due date. You just have to let me know how much more time you want to move it. Same deal for the Unit 1 ones. Those are set for this Sunday. I know that's a wicked turnaround. I just need to know what I should be shifting it to. Okay? Unit 1 is old content now. That should be spending more time reviewing that to try and make sure you have those strengths so those don't turn into weaknesses later on in the semester. Okay, so we do want to try and get through those as fast as possible. But at the same time, you do also want to make sure you understand what's going on behind those topics. Okay? In theory, you've studied each of those topics for Unit 1. You've also now been tested on them. So you've received all of the content that you would get. So attempting all of those this week, I think, makes a lot of sense. Okay? And see where you're falling with those and see how you're doing. Does that make sense? The next ones is where we're starting to move into kind of review content, because we said we still have some topics to cover. Okay, and then looking at some new topics. Quizzes are timed at the longest, I think, is 10 minutes. Most of them are sitting in the 5 to 6 minutes. So it's not a sit there and let me go figure out how to do it. It's, do you know how to do it? Kind of make sense? You can still have notes. It's not like it's a closed note thing. But it's trying to test you on what you know. Make sense? Okay. Some other things I'll point out. You can't look at anything as far as the quizzes go. You see it and you're done. Okay, that's kind of one of the caveats of me getting to use these at all. They're trying to keep tight control over these systems. They spend a lot of time generating it, which means it's kind of a one and done system. You can absolutely come back and say, hey, I struggled with the question on it, and with me, I can open it up and say, this is the question you had, and we can go through and talk about that. I have no problems with that. but it's not just going to be widely, openly available. Make sense?
So are they multiple choice?
They're all multiple choice. Multiple choice and a little bit of short answers. So some are drawing. I think the resonance one might be a drawing one. So what you would do is there's a link, you click that link and it takes you to a drawing software. You would draw your answer there and it spits out a code. That code you enter into the quiz. And as long as the code matches, you get credit. I don't know how much I trust that code, so for those kind of questions, what I'll do is take your code and copy it back into that software and see what it spits out and see if I agree. Like maybe it just didn't grade you right for what you drew.
Do we have to scan it?
There's no scanning.
Because it takes time.
Yep, nope. It's still gonna take time because what'll happen is you click it, it takes you out to a new website. You have to draw your answer in that website, but then the website spits out a code. You copy that code back into the Canvas assignment. Okay? I'm very nervous about it. Okay. That's probably the number one issue I think with OChem is drawing software. I'm very nervous about that.
Could you stay more time for the questions?
I did. Yeah, I did add a few more minutes on those for those reasons. But yeah, I tried to build them all at 2 minutes per question. And then those, I think, were double time. I think those went up to 4 minutes for whatever question required drawing. So it's still a, do you know what the answer is? Let me draw it so I can prove it and put it in. Make sense? Okay. Questions about the exam?
How could we improve the grade?
What? So how do you improve the grade is right here. That's that unit 1. Okay. That first module has 9 quizzes in it. They're each worth 1 point. To improve your grade, you have to get a perfect score on that quiz. So it has to be exactly 1 point. And what I will do is take those points and I'll add them into your exam grade.
So the maximum just 9 points?
If you do all 9, I'll give you a bonus. A bonus free point. Just for completing all 9, not necessarily getting them full credit. So if you complete all 9 but only get full credit on 5, I'll give you 6 points. Make sense? Other questions? Questions about the exam itself? I will highly encourage you to come to office hours to ask questions about the exam, figure out why you got questions wrong. It is still possible there's typos. I went through it and kind of carefully regraded things. If you look real carefully, your Scantron score might be a weird decimal. Only might be, but it's a weird decimal because of the multiple select answers. So I gave partial credit for those, and I gave some partial credit for the bulk answers as well. That is not reflected on the Scantron because the Scantron itself can't do that. I have to do that kind of manually on the back end. So theoretically, if you can read the score on the Scantron, which I doubt you can, well, maybe you can. If you multiply that by 2, your score is probably, not guaranteed, but it is probably higher than that on the actual exam itself because of how I added points back. Make sense? Yes, sir.
And when will we be able to see our scores in Canvas? Like after these quizzes?
I just after these quizzes?
You'll have an updated scores for everyone? Or?
Yeah, that's going to come down to what due date we're going to put on this. I can probably do it, like if you max it out, let me know, oh, I think I got them all perfect, then I can add that point into your exam score without a problem. It's going to be more an issue if the class or one or two people drag it on through the whole semester.
Okay.
So that's more just letting me know, and I'll track it. Other questions? Okay. A couple things I'll add for what was given to you on the exam. First page, periodic table is the only thing you're getting on the next exam. So you're going to lose the priority for naming. You're going to lose all those functional groups. So those are things that you need to know now. The classifying a pair of molecules flowchart. I'm willing to give that to you. I don't want to, but I'm willing to give that to you. I think it's a bad idea to reference it because it's going to slow you down. But I will include the classifying of paramolecules flowchart on your next exam. But functional groups and naming of functional groups, you need to know all those pieces. And the closer we get to the second exam, the more I'll remind you of those things. So we'll try once more. Questions?
Meaning you'll like explain.
Yeah.
the
Oh,
question.
yeah.
Okay, 25. I guess the citizen trans thing doesn't necessarily 100%
And cis and trans, you'll note, is something that we're going to be talking about in this unit. This is a question I did some kind of points back on. I'll admit I don't remember what that was off the top of my head, but I did do that for this particular question because 25 was commonly missed. Oh, because it's here, I'm going to ask. Fairly covered content for the point of the semester? Okay, I was shocked everybody said true. Okay. Just thought that was interesting. I mean, it's a smaller class. Maybe you feel you can't hide. But I've asked that question before. Things where I think it fairly covered. And getting varied responses. But yeah. Yeah, that was one that I had in the key as false, as B. And like everybody got it wrong. And looking back at it, I was like, what the heck happened here? And I was like, oh, it's that question. I had to grade it by hand anyway because I was going to accept either answer. I was like, oh, well, that's an easy fix. I'll just switch it to A. And now everybody's got credit. Like, that was a bit silly. So, any case. You said specifically, I believe, you're concerned about E and Z.
Yes.
Okay. So we won't stress about the rest of the details behind this. We'll just focus in on E and Z. So when we're talking about E and Z, what we're talking about is the double bond and where the highest priority groups are located around the double bond. One of the things that you may notice that I just drew in, and actually I'll do it in a different color, is that I'm going to draw in these blue bonds. Okay, those blue bonds are going out to hydrogen. They were not shown. Why were they not shown? They're implied. Okay, so we are absolutely allowed and okay to imply them. We don't have to show them. But when assigning E and Z, it is very helpful to have those. Okay, because it can help us see it. The next thing that I'll point out within that is that if we look, what angle is in there, in that green space? What angle does that look like? Looks like about 120-ish, okay? It's supposed to be hitting exactly 120, but we may not be perfect, okay? Why do I want to draw it as 120? That was not what was supposed to happen. and not say, I don't know, something like this. Where now, I don't know, we'll call that 10 degrees. Why do I want to draw it as 120 and not 10?
It'll change the whole molecule or compound.
So sort of it'll change. What it's going to change is not the compound. It's going to change our drawing and our interpretation of the molecule. The molecule does not have a 10-degree angle there. That molecule is going to hover around 120. Why is it hovering around that 120?
Because that's, I guess, the shape of it.
Okay. If we look at the carbon atom at each of those points, we could look at either one of them. We could look at the three groups of, or the number of groups of electrons around it. It has three groups of electrons. Three groups of electrons means trigonal planar, and trigonal planar means 120 degrees. All of that becomes implied in our drawing. This is one of the reasons why we have to be able to identify that information. Why does it become important to us? Well, it becomes important to us if we're going to assign E and Z. Okay? The first thing we do when we go through and assign E and Z is we cut the molecule in half, I would argue, okay, this direction, and we look at both halves, independent of the other. Okay? So I'm going to look at the right half, and I'm going to compare hydrogen to whatever that blue atom is. What's the blue atom, the blue dot? It's a carbon. And what I want to do is assign priority to those two atoms. So number one, is there a difference between the atoms? Is hydrogen different than carbon? Yes. Because there is a difference, I now have to assign priority. How do I assign priority? The heaviest atom gets the priority. Okay? And we may encounter systems where it's not inherently obvious right away, and if it's not inherently obvious, we go one further atom further away and one atom further away until we find that difference. Or we find out there isn't a difference, in which case we can't answer this question. Okay? But we do see a difference between those. The carbon at the bottom is a higher priority, so I'm going to go through and star that carbon as my higher priority. I'm now going to go through and look at the other half of the molecule, again branching out from the carbon of my double bond, and I'm going to see that I've got a carbon and a hydrogen. In this case, someone labeled this what looks to be a 7, but I think they're trying to call it a 3. Okay. Is there a difference between carbon and hydrogen? Yes, which means there's a priority difference. We have to assign that priority difference. Which atom has a larger atomic mass, carbon or hydrogen? Carbon. I will go through and I will star that again. Now what I'll go through and do is cut the double bond in half parallel to the bond through there, and I now want to see where my stars are. Are my stars on the same side or the opposite sides of that line? Opposite sides, which means I have a trans double bond, and a trans double bond gets what label, E or Z? E. So with that information alone, we could eliminate both B and C as answers, and we're down to a 50-50 coin toss. That 50-50 is now assessing between the rest of how we'd address that name. The more I think about this one, the difference between those two names ultimately came down to which one you place first in the name. Yeah, whether it's the alkene or the halogens. Okay, so the A as an answer choice said the halogens were more important, which gave them the lower numbers. If we look at D, the alkene, 2-ene, we gave the alkene a higher priority. And what Lindsay's doing, I think, is looking to the front to see the higher priority, the rankings for our naming. And when we look at the priority for our naming, alkenes are higher priority than our halogens, which then means the alkene has to get the lowest number. So we'll assign this one D. This is one I think I gave half credit for A, maybe even full credit for A, because it's really on that line of priority differentials. So unfortunately not, because the Cl and the bromine aren't really on opposite sides of the double bond. They're on the same side of the double bond. They're on this top side. Okay? They're on opposite sides of this sigma bond, but we don't reference cis and trans about sigma. Why not? Why does it not matter? Why is sigma not relevant to be referencing cis and trans for, but our pi bonds are relevant?
Because you can move them.
Right idea, I don't like the word move. Can you do better than move? It's a rotation. Okay? Remember when we talked about hybridization, the sigma bonds could freely rotate because the overlap of those orbitals won't change as you do a rotation. With the double bond, we're talking about a pi bond, and when we do the rotation, you would break the overlap of the p orbitals, which is why the pi bond can't rotate, which is why we have to reference cis and trans. Okay? So cis and trans is something that's focused primarily on double bonds. Okay, there's one other case that you can use them for, and that's for ring structures that are small enough that they can't do an internal rotation, which for the sake of this class is going to be all ring structures. Okay. Some ring structures, if you make them large enough, can rotate internally all the way around, but it's a rare system for us. Make sense?
And then for 26, was A the correct answer?
Well, this is actually convenient. There's that trans. Okay, so we can use cis and trans for ring structures because they can't rotate fully around. So if we're going to do trans, we need an up-down. So in A, there's one bond up. There's that bond aimed up, which would mean that structure is cis. That's not the trans structure. Is A the lowest energy? Yeah, because they're both equatorial, but it's not what the question asked for. It wasn't just which of these is the lowest energy, it's which of these is the most stable chair conformation for the trans 1,3 dimethyl cyclohexane. A, unfortunately, doesn't match that. Okay, it's not trans, it's cis. B gets us trans. C gets us trans. D, whoops, yep. D gets us trans. Okay. What other information do we need to look at? It has to be 1, 3. If we go through and look at D, there's 1, 2, 3, so D works. C, 1, 2, 3, 4, that's the 1, 4, so that doesn't work. And then in B, also 1, 2, 3, 4, B doesn't work. So B, C cross out, and the only answer we get left is D. Okay. Organic is one of those dangerous things that pretty much every piece of information is useful. You have to consider almost every single piece of information. Okay. You can't just jump on one word to answer your question. Other questions? I'll let slide with one more, or we can move on. Okay. Back to kind of our chiral atoms, okay, or stereochemistry. What we're looking for is forms of asymmetry within the molecule. For structures like both of these shown, that asymmetry is a little bit easier to see, okay? but it does require that we know another piece of information. So for instance, if we looked at the top structure, we could compare it to those in red. Okay, and when we compare it to those in red, that's effectively the same system, and yet in red, there's no asymmetry. Okay? These two molecules are identical, and these ones are not identical. Why are they not identical?
Because the atoms are in not the same place.
One of those places or definitions for identical is that the structures must be superimposable. And there's no way that we can superimpose the structure on the left on the structure on the right. But we can for these other ones. Why can we for the new structures I drew?
We can imply it's carbon.
No. I'm going to point to you because you literally just asked this question. You may not have realized it.
Because the sigma bonds, right? They have to stay there, or they can't rotate.
Right idea, wrong words. The sigma bonds can rotate, and that's how we can switch from one conformation to the other. Okay? Whereas the double bonds is a sigma and a pi, and the pi bonds can't rotate because we lose that p orbital overlap. Okay? So the structures on the right with sigma bonds, I am allowed free rotation. It allows me to get into a configuration where they look identical and therefore, or they are superimposable, therefore they are considered superimposable at all states. Okay? For the other compounds, there's no way we could possibly overlap those two structures without breaking the pi bond first. Since we're not allowed to break the pi bond, those are not identical. Okay? A question that might come up, why did I not call them different? Different has a very particular meaning. The meaning of different is that they have different chemical formulas or not the same chemical formulas. Those two drawings have the exact same chemical formula, so they aren't different. That doesn't make them identical, that just means they're not identical. So you'd have to further nuance where that difference lay and what defined relationship you would get between those. Right? You could think of it as, I don't know, identical as couples and not identical as single people. Okay? But if you're dating, are you a couple or are you still a single person? What if you're seeing somebody else on the side? Okay? There's a gray area that floats in that transition, and so that would carry a new label. That's where the flow chart comes into play and figuring out exactly what that label becomes. Okay? The two ring structures down below are what we just kind of addressed with cis and trans because we can't do an internal bond rotation. Okay? And this comes from actually playing with the model kit, which I don't have, but you can do it with kind of just your hands. If we open up a ring, we can rotate all the way around with some limit because your hand kind of breaks eventually. But you can rotate all the way around. Can I do that same rotation if I make a ring? I don't even know how to pull that off, right? Because your hand starts to lock up. I can't fold my other hand inside through that loop. The ring structure prevents internal rotations. So you can kind of oscillate back and forth, but since you can't do that full rotation, you can't exchange the cis-trans alignment. Okay? So those are, the cases on the left are systems of asymmetry. Okay? We've lost a line of symmetry within the molecule. Okay? Cases on the right, we have a symmetry running right through there. You can see that we reflect across as a mirror image. Okay? You could also see a real goofy one here, a point symmetry running through that point to reflect across. It's not an easy one. I don't recommend that one. The other one that you could see is actually through the plane of this drawing. Okay? We just cut straight through. We wouldn't be able to do that with any of the other structures to get that same symmetry. Okay? So what does that mean for us? That means we have to introduce other terms where we can bring in cis and trans and things like that. Okay? There's a word floating in the back there that just got kind of overlapped incorrectly. This is saying geometric isomers. Okay? Your geometric isomers are in reference to your alkenes. I care less about that term, so it's not a big deal, but it does potentially show up. Where it becomes a lot trickier is officially down in this bottom structure with our rings, okay, because it's harder to see those kind of alignments in those positions. So those rings kind of bring in the reality of where that asymmetry is, and that can come in through what is known as chiral atoms, stereocenters, chiral centers. They're all effectively referencing the same thing, but to, again, slightly different definitions. For the sake of this class, and ultimately for any OChem class I would ever teach, use those terms interchangeably. Okay? So what we're looking for is something that prevents that line of symmetry. Okay? If I take a look at that top example, okay, what we're doing is reflecting across through a mirror. And if I reflect across through the mirror, that would be the resulting structure. But what can I do with this structure? I can just rotate it in space so that it still superimposes, because I can't tell a difference between the threes. Exact same color, exact same number. Does that make sense? Okay, so those are symmetric. Okay, the line of symmetry in that one is a hard one to go through and draw, but let's change our viewpoint on this. Green, blue, red, and red. That mirror, or that line of symmetry, is actually slicing through the plane of the paper. You get the R group coming at you, the R group going away. The paper itself is the mirror plane where you can reflect across. If we turned this molecule a little bit, both of the R's would be turning at us, and this blue would be aimed away. Where's the mirror? It's a perfect slice straight through the middle of those. That would be your internal mirror plane, your line of symmetry. Kind of, sort of? So let's try a new pass. How easy is it to see lines of symmetry? Okay, I'm going to take silence to mean it's not very easy, and I would completely agree with you. Seeing lines of symmetry on a particular drawing can be very, very challenging. So what we would want to look for is other things to help key us off. Okay? One of those things is that if you have a carbon atom with 4 groups, and it will only really happen with atoms that have 4 bonds, or 4 groups of electrons, look for 2 things that are the same. There's a line of symmetry within that molecule. Whether you see it or not is irrelevant. There is a line of symmetry. But what happens when you move to an atom with 4 different things on it? This is supposed to be blue, and that's supposed to be purple, for the record. Okay. Can you get a line of symmetry? And what we'll find is there is no internal line of symmetry within that molecule. Because it has lost that symmetry, we can refer to it as an asymmetric molecule. Okay. That means the molecule itself is chiral. Okay. Why did we invite a new word for it? Because we can. Okay. And that chirality means that if I draw its mirror image, there is no way that I can spin, flip, rotate, or turn that mirror image so that it superimposes on the original structure, which is exactly what we did with the top one. Kind of, sort of? Not an easy process to nail down. Okay? That's why what we do is tend to look for the atom with 4 different things bonded. If we have an atom with 4 different things bonded, ta-da, there, we know the molecule is chiral. For the most part. For the sake of this class. I'll keep it at that. Kind of, sort of?
So you can basically say that all chiral atoms are non-superimposable.
Have non-superimposable mirror images. So it's always referencing the mirror image. Okay. And is it perfectly true? It's not. For the sake of our class, I will make it true for any test question I ask. Right? So if you're going to go out into the world and try and find other things, there are exceptions to that. And I think the next slide shows one of those exceptions. If it's not the next slide, it's coming up soon. It's coming up soon. It's a little ways out. Okay. Here's another viewpoint on those structures. This is exactly what I talked about. You can turn the molecule. There's the line of symmetry on this running through. It only has 4 groups. It has 2 whites. Since they're both white, that counts as 1, 2, 3 for the green and the red. That only had 3 distinct groups. There's no line of symmetry. If we tried that same thing with something that had 4, I don't have that line of symmetry running through the middle, because what happens? White would reflect to yellow. That's not the same. Kind of make sense? Okay. The definition of looking for those mirror planes or our line of symmetries is technically a good one. It just sucks to find it. Okay. Some people are really good at it and just lock onto it and it becomes easy and they just don't understand why anybody else can't see it. I'm not one of those people. I've had to work really hard to be able to look for lines of symmetry within molecules. And even then, I'm only slightly better than 50-50 at picking them out. Okay. Other things that can make things tricky. Okay. What we looked at were examples where we had tetrahedral structures. And with tetrahedral structures, we would see wedges and dashes. Okay. That could be a big red flag that we're now looking for a chiral molecule. But do we always have to show wedges and dashes? Do I have an atom with 4 different things? Yeah, I do. In fact, I have 4 atoms with 4 things connected to them. One of those 4 atoms has 4 different things. Okay. Which atom is it? Is it our blue carbon, our purple carbon, our red carbon, or our green carbon? It's the purple. But I only see 3 things. We have to remember that implied hydrogen. That implied hydrogen is still there. Why are we not showing wedges and dashes? Okay. It wasn't relevant to the question that we were asking about at the time, so we didn't care to show wedges and dashes. This is just the skeleton structure. Okay. It's not important to me whether it's chiral or not. All I'm focusing on is the basic core structure behind it. But it does mean that if I happen to now change my focus on it and say, well, now chirality is important, I have to realize that there is a chiral atom there. So I have to be able to identify it. Does that make sense? Okay. So wedges and dashes should be used when looking at chirality. That doesn't mean we'll always use them. Okay, because it's going to change depending on what our purpose is behind it. We could push further. Do we have any atoms with 4 things connected to it in the bottom structure? That carbon only has 1 thing bonded to it?
2.
What's that?
1 hydrogen, right?
It has 3 hydrogens bonded to it. It had to have 4 bonds. So it does have 4 things connected to it. Are they 4 distinguishable things? No. So very subtle change in how the question comes out. Okay, so we have to be careful behind that. It's not going to be a chiral atom. But if I want to show the shape now around that carbon, I could go through and show wedges and dashes. Does that mean it's now chiral? No, it just means I'm trying to show the 3-dimensional characteristics around it. Okay? So be careful with wedges and dashes. Wedges and dashes do not mean chirality. They mean a shape. That shape is particularly important when we look at chirality, so that if our focus is chirality, we almost always see wedges and dashes. But even then, we may not care about it, and so we may not be specifying it explicitly. Okay? Which is nasty, because sometimes we choose to use it, sometimes we don't. Okay? And it all depends on the context. But the context is something that you haven't learned yet because you aren't organic chemists, and you probably never will be. So it's recognizing some of those patterns and some of those complications behind it. For the sake of the class, I will try to flag them, at least when we're talking about it in class, but you could see an exam question where it's identify a chiral atom. Because here what I'm asking you to do is to be able to take it to that next level and interpret those line structures, those skeleton structures, to say where a chiral atom would be. Kind of, sort of? Okay. When we bring in our chiral atoms, okay, we're going to start to get relationships between things. So when we talked about our structural relationships, we've talked about different and identical geometric isomers. Okay. What we'll find is that that chart explodes, and that's what our next slide goes through and shows, and looks at all the individual relationships. Okay. So we've got lots of extra pieces to come out of this. We get our raw definitions behind these. Enantiomers are structures that are non-superimposable and mirror images of each other. Okay? So they had to have a chiral atom. They would be chiral molecules. Okay? Diastereomers are structures that are non-superimposable but are not mirror images of each other. Where are these relationships, as quick examples, going to come from? These two structures are mirror images of each other. Where was the mirror that I placed around the red structure to make the blue structure? Said another way, did I place a mirror here? Cool. No, those are definitely not mirror images there. Where did I place the mirror? Like here? But if I place it there, what happens to the wedge? If I mirror it across, what would it be? It would still be wedged. Horizontal this way. If it's wedged and I horizontally go, it's still wedged. This one is impossible for me to draw. Where is it? It's actually behind the molecule. Okay, so if my bromine's here and I now put a mirror over here, what happens? Well, this part of my hand, my pinky, is what's reflected across first, and now the bromine's aimed the other direction. So the mirror plane was the one placed immediately behind it. Was that easy to see? No. So if you're trying to draw, if you're asked just draw enantiomers, pick the one that's easy for you to see. Okay? Okay? And based off of Kimball's initial response right away, whoops, I would argue the mirror that's easiest for most people to see would be this one. Okay? How did we get this? We placed the mirror right next to it. Okay? How do I make this purple structure the blue structure? Well, if I take this purple structure and I flip it over, what happens? The carbon chain would align. What happens to the bromine if I flip it over? It goes away. There's the dashed line. Kind of see those relationships? Okay. Those relationships take practice to manipulate, and I would argue are all about the model kits. Okay. When we move to diastereomers get a little bit trickier. I'll put a bromine there, kind of out of space, and I'll put a bromine here. You can't read through those words. We're going to lose the example here in a second. I don't know why I decided to color it differently. Okay. So these ones, the bromines are all connected in the same space, but their orientation in space is slightly different. Okay. In one case, the bromine didn't change. It stayed that wedge. The other case, it went from dash to wedge. Wedge to dash. Dash to wedge. That's a reflection. That's a reflection through the plane in front of us. Okay? That dash being aimed back, if we now have that mirror plane, it's now that bromine aimed at you. So we mirrored that chiral carbon. But what did we do to the other carbon? We didn't do anything to it. Okay? And if our structures are true mirror images, everything mirrors. Not just one part, everything. Which means these can't be mirror images to each other, but they're also not superimposable. Because if I tried to slide this over on top, the bromines, the blue bromines, wouldn't overlap. The red ones would. Okay? What's an interesting feature that comes out of our diastereomers? Well, enantiomers, we only need one chiral atom to be a stereo, or to have a stereocenter to have enantiomers. We can have more than one, but we only need one. Diastereomers, you need two. You have to have at least two. Okay? So that's a nice subtle shift within our structures that can help us flag diastereomers over enantiomers. Okay? It's not perfect, and this is, I've got to erase the diastereomer structures now. And it's not perfect because when we move to meso are structures that have two or more chiral centers also. Okay? But they are superimposable on the mirror image. Okay? Mesos are a really special case of identical molecules. Okay? So they're two structures that are superimposable and they're mirror images to each other. We would just call them identical, but we're trying to flag the extra chemistry associated with them, that they have chiral atoms within them. Okay, so we're adding an extra layer of information behind it. The meso category is the one that I will try my best to not ask questions about. Okay? Because that's taking it kind of a step beyond our enantiomers, diastereomers, and everything else. Okay? It's the one that I was referencing 5 minutes ago saying I need to not ask questions along those lines. So if you're seeing chiral atoms, you're going to fall in either this enantiomers or diastereomers category. Okay? Chiral atoms can show up in the meso, but the molecule itself is achiral, as in not chiral. Okay? So those are our hardcore definitions. I never found the definitions useful, which is also why I tend to not like textbooks on this topic. Okay, because ultimately what you're being asked to do is to identify the relationship between multiple molecules. That's the point of this unit, or this section in most chapters. So what we would do is take a look at two molecules, and we try to identify their relationship. And that's the point of this flowchart. Do they have the same molecular formula? No? Well, then they're different. If yes, then I have to ask another question. Are they superimposable? If they superimpose on top of each other, well, then they're identical molecules. I can call it identical. What's the problem with that superimposable question? All sigma bonds can rotate. The drawing itself may not look like it superimposes, but we have to realize we have to give it time to be able to deal with that rotation. Make sense? That sets us up with identical. If we also had two chiral atoms, we have meso, that's the category we don't have to stress about. If they're not superimposable, we could call them isomers, and that's where we look for the same atom connectivity. Okay? If no, they're structural isomers. Okay? So the atoms, we may have all the same atoms, but we've arranged them in different spaces. Those now become structural or constitutional isomers, depending on the textbook or instructor that you have. If they have the same connectivity, we could call them stereoisomers. We can refine that further by looking for a chiral atom. If no, they're now geometric isomers. That's our cis-trans systems. If yes, we're now evaluating, are they mirror images to each other? If they are mirror images, they're enantiomers. If they're not, they're diastereomers. This establishes a flow chart that allows you to kind of logically move through each of those pieces without having to be like, well, are they enantiomers? Well, dang, no, they aren't. Well, are they identical? I don't know. And if you jump around to each of those kind of endpoints, it's hard to kind of track in a logical flow. That's why the point of the flow chart is to try and organize your thought process through it to make it a little bit of a more streamlined process. Eventually, you'll see people just be, oh, those are enantiomers, because they recognize those relationships very, very, very quickly. Okay, and ultimately what they're jumping through is formula, superimposable, atom connectivity, very, 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 very fast. And they're able to internalize that. Kind of makes sense? Okay. Do you want a little practice? Yeah? Okay. We've got 4 structures up here. Identify your relationships. First thing I'll ask, just by kind of looking at it, do they look different at all? What's your gut response? Do they look different? Okay. Okay. I tried to draw them in a way that made them not look different. Okay. So I do find it interesting that you're like, oh yeah, they're all different. Try and piece it out. So what did I just draw? 6? Yeah, we got 4 relationships on the outside and 2 on the inside. See what you can come up with. So I've added some color coding. I also went through and wrote the kind of list of questions. So same molecular formula. Okay. Yes, this can be hard to kind of go through, particularly if you're uncomfortable with structures. It just takes time. You're just looking. What I'm looking for is big pieces. Okay, so I see a ring with a double bond. All of them have the ring with a double bond. I see 2 OHs. Okay, I see a methyl straight up off the top, which is fine. I see a little branching thing at the bottom, and then multiple branches, and that one might be a little bit weird for me, but all I've done is moved that CH3. So they do indeed have the same molecular formula, at least to my first glance, without actually having to write out a formula for it. What I'm trying to do is just match pieces. Superimposable, no, I would argue none of them are superimposable, so I can move through that. Atom connectivity, and that's where that red one's going to come into play. Okay, that red one, I moved that CH3. I took a CH3, if we look at the orange dot at the bottom, I took that CH3 and I put it where the orange dot was. What did I remove from up here? Hydrogen. I took a hydrogen off here so I could put the methyl there. I exchanged the methyl for the hydrogen, 2 different spots. Okay. So do I have the same atom connectivity? No, the red structure has a different atom connectivity than all of the others. Okay. Because of that, that red structure is now going to have a different relationship. The conclusion of the atom connectivity being no is that those are now structural isomers. Make sense?
Do you want us to put that they're constitutional too, or can we just use it interchangeably?
Frankly, where it's going to come into play is the multiple choice. And so you would have those words there. My reflex is structural, clearly. Probably because I can spell structural better, if I'm going to be honest. But depending on where I pull the question from, if it's a question I wrote, I'm going to write structural. If it's a question that I'm pulling from a test bank, they might have constitutional. So it's something that I try to always add both words, but it doesn't always work out. So that's why I try to put it in the chart as both, which I'm fully aware of is kind of a cop-out. Chiral atoms, yes. Okay, I'm seeing wedges and dashes. Okay, that doesn't mean they're all chiral atoms necessarily, those wedges and dashes. Okay, but I'm also now limiting. I don't have to worry about the structural isomers anymore, and I can just focus on my purple, orange, and blue. Okay, I'm seeing those wedges and dashes, and then I'm quickly just saying, can I tell a difference between these two? Yeah, one's got a double bond, the other one doesn't, which means I got 4 things there. So yes, I've got a chiral atom. And I can do that real quickly at each of those spots, okay, to trigger that thought process. The other chiral atom within the structure is a little bit harder, okay, but at this point we're not being asked how many, we're just saying, is there a chiral atom? So if there is one, yes, jump on it. Okay. Then we move to the mirror images question. The mirror images part is going to be a bit of a challenge. Where I would shift personally is looking not at the mirror images, but the anti-mirror images. So this structure on the right, okay, wedge, wedge, dash wedge, dash wedge. Okay, so if I went through a mirror, it's going to shift, particularly if I'm maintaining the overall structure. So what would that suggest? This top one hasn't passed through a mirror image. So it is not the mirror image of either the blue or the orange structure. So if it's not a mirror image, its relationship is? Good pronunciation. Most people call it diastereomers. Okay. But yeah, diastereomers. Right, now moving to the orange and blue, I might reflex, again, depending on how much time I've got on an exam, I might reflex and just call them enantiomers and hope for the best. Okay, but officially they have to be mirror images of each other. Okay, where is that mirror plane between the orange and the blue, if they are indeed mirror images? Did you say on the right?
Yeah.
Okay, so.
No, I mean behind.
Oh, behind. Thank you. Yes. Okay, it's behind. And if that's one of those things that you can't see well, that's fine. Do it on the right or left. Here, I'm going to draw it in on the left. So I'm going to say I want to know what the mirror image is for my blue dot. So if I'm going to draw the mirror image, I'm going to have that hexagon. This isn't going to change down here. Where should I place the double bond? The left or right-hand side of my new drawing?
Right.
The right-hand side, because where the mirror reflects across. It's closest to the mirror. Does that make sense? That means the methyl's up. What happens to the OH?
Yeah. It's coming towards us.
Okay. So we've got 2 explanations. Number one, which side of the structure it's on. So Annie, I believe you were saying it's on the left-hand side. I agree, our OH does need to be over here. Now the question is it coming forward or away? Okay. Where our mirror is placed is vertical. Our OH is currently going away. So if it's away and I pass it through the mirror, what happens? Does it switch? It stays the same. The only time it switches is when you're doing that mirror either in front or in back. That's when it switches, which means this OH needs to stay dashed. Does this blue structure look like our orange structure down here? Okay, thank you, Kimball. I accept that. And Annie, you're doing a great job. You're not wrong, but I would argue that I would agree with Kimball. No, those don't look the same. Okay, so what I want to do is change the orientation. For me, what I look at is that ring structure. I've got the double bond on the right hand of my molecule, and in the orange structure, I've got it on the left hand. So I'm going to take this molecule, and what am I going to do? I'm going to flip it over. Okay, so I want to flip this. These 2 I know are enantiomers. That says enantiomers, trust me, I'm just running out of time. Okay. Now what happens when I flip it? So again, I'm going to keep my overall structure, my ring structure. If I take this structure and I flip it over, where's the double bond now, right or left? It's left. Methyl doesn't change. Where should the OH be, right or left?
Right.
Should now shift to the right. So it's here, and I flip it over. The OH over here, flip over, should be on the right-hand side. So I have my OH up here. Should be wedged or dashed? Dashed means it's going back, right? What happens if I flip my hand over? Damn. This is one of those spatial things. It's really hard to deal with. Okay? Why I push the model so much. That dash, if I flip the molecule over, is going to become wedged on the other side. What happens at the bottom? Well, I'm still going to have those. It was at us, and then what did I do? I flipped it over, so it's now back, and we show back with a dash. Can I see the relationship between the black orange structure and the orange structure? Yeah, what's the relationship between those two structures? They're identical. What's the relationship between the blue structure and the orange structure? These two. What did I do? I didn't mirror. I just flipped the molecule. I just did this. That doesn't change the identity of the molecule. It just changes your viewpoint on it. Depending on your perspective, better or worse. Okay? Identical. That was a bad joke. Whatever. Okay? So if orange dot to orange is identical, and orange to blue is identical, and blue to black is an enantiomer, what is blue dot to orange dot? Blue is identical to orange. What is blue to orange dot? Orange dot to orange is, orange to blue is, what is blue to orange dot? This is identical. This is identical. What is blue to orange dot? Identical. Said another way, we've got this orange dot. We're saying this is equal to orange structure. And we know orange structure is equal to blue structure. What is the relationship between orange dot and blue structure? They're identical. That's what the equalities all mean. Okay. What is the relationship between blue dot and black? So orange dot to blue structure is identical, and then blue structure to blue dot was what? And if blue structure and orange structure are equal, what is the relationship between orange dot and blue dot? They're enantiomers. Okay. We're beyond time, so we're going to wrap it up real quickly here. Did you just realize how hard that was? That's very challenging to nuance each of those individual steps along the way behind those processes. That takes practice to recognize the flow of that thought all the way through. So what we tried to do with the equalities down below so that we could see those relationships. But our blue dot to our orange dot are indeed enantiomers. And we answer that by doing what we know to be enantiomers first, and then we say, how does that change to look like the other one? Or what we can do is take our structures and say, how can I arrange them to find the mirror image? It's up to you how you decide to navigate that path, but it is a challenging path to get through. Okay? With that, I'm going to go ahead